Secrets often escape protection through surprisingly ordinary sources. One common culprit is version control systems, where developers accidentally commit credentials into repositories, leaving them visible in code history forever. Configuration files with embedded usernames, passwords, or tokens also create lasting exposure risks, especially when shared among multiple teams. Continuous integration and continuous deployment (CI/CD) pipelines often store secrets in plain text within environment variables or build scripts, inadvertently giving every automated job full access to sensitive material. Container images may carry configuration layers containing secrets, while third-party integrations such as payment gateways or messaging APIs can require credentials that get embedded in deployment artifacts. Each of these sources becomes a potential leak point, showing how exposure can stem not from malice, but from convenience and haste. The consequences of poor secrets management extend far beyond a single compromised file. When credentials are left unprotected, unauthorized individuals can gain direct access to production databases, application servers, or storage environments. Attackers can exploit exposed tokens to impersonate legitimate services, conduct supply chain attacks, or pivot laterally across connected systems. A single leaked API key may allow attackers to exfiltrate data or deploy malicious code in the name of a trusted process. Beyond the technical damage, such failures erode customer trust and may invalidate audit assurances under SOC 2. An organization that cannot prove control over its secrets signals a deeper weakness in governance, potentially leading to regulatory consequences or lost contracts. To prevent these scenarios, organizations must focus first on visibility through secret discovery and scanning. Automated scanning tools can be integrated directly into the development workflow, running before commits, during CI builds, and continuously in production repositories. These tools search codebases, configuration files, and commit histories for patterns matching known credential types. They can also monitor public repositories for accidental disclosures that occur after deployment. When a potential secret is detected, the system should trigger an alert and automatically revoke or rotate the affected credential. This level of automation limits the window of exposure, ensuring that detection leads immediately to containment. In SOC 2 terms, this proactive discovery supports both the logical access and change management requirements of the trust services criteria. Prevention, however, must accompany detection. Strong guardrails stop secrets from entering code in the first place. Commit hooks can be configured to block credentials from being pushed to repositories, acting as a last line of defense before exposure occurs. Peer reviews of configuration files ensure that sensitive data never slips past human oversight. Developers are encouraged to use placeholder variables or template references rather than hard-coded values, maintaining clean and reusable configurations. Exceptions and false positives should still be monitored carefully to refine these safeguards without impeding productivity. Over time, this blend of automation and human review fosters a security-aware development culture, one that treats secrets as living assets, not just text strings in code. Centralizing secrets into vault-based storage systems represents a major leap forward in maturity. Tools like HashiCorp Vault, AWS Secrets Manager, and Azure Key Vault allow organizations to store sensitive credentials in encrypted form and control access through granular permissions. These systems serve as a safe deposit box for digital secrets, ensuring they are never hard-coded or stored in plain text. Read permissions can be restricted by role and environment, for example, allowing developers to access only staging credentials, not production ones. Every access request generates a detailed log entry, enabling audit tracking and version history. By using vault-based architectures, organizations satisfy multiple SOC 2 criteria simultaneously: confidentiality through encryption, integrity through logging, and accountability through access control. Dynamic secrets and ephemeral credentials take protection one step further. Rather than storing long-lived passwords or tokens, systems can generate short-lived credentials that expire automatically after a job completes. For instance, a CI pipeline might request a database password valid for only a few minutes, after which the credential becomes useless. Automatic rotation after each build minimizes the risk of unauthorized reuse. Static passwords in configuration files become obsolete, replaced by runtime-issued credentials retrieved from the vault. This dramatically reduces the blast radius, the potential impact of any single compromise. Even if an attacker captures one credential, it will expire before it can be abused meaningfully, transforming secrets management from a static defense into a dynamic, time-bound safeguard. Integrating secrets management directly into CI/CD pipelines ensures that security does not rely on human memory or manual intervention. During pipeline execution, secrets can be injected securely as environment variables fetched in real time from Vault APIs. These values must never appear in build logs or console outputs. Instead, they are masked automatically to prevent accidental disclosure. Once a deployment completes, the system should revoke temporary tokens immediately, ensuring they cannot be reused. This model creates a seamless, automated chain of trust from code commit to production deployment. For SOC 2 audits, it provides clear evidence that secret handling is embedded within the SDLC, not treated as an afterthought or ad hoc practice. Like encryption keys, secrets must follow a well-defined life cycle of rotation and renewal. Organizations should define rotation intervals based on the sensitivity of the secret and the privilege level it grants. Critical credentials, such as those providing administrative access, might rotate weekly, while lower sensitivity tokens rotate monthly. Automation through scripts or Vault schedulers ensures these rotations occur on schedule without manual oversight. Verification of rotation events and dependent system updates provides tangible evidence of compliance. Maintaining a documented chain of custody showing who approved each rotation and when reinforces operational accountability. In SOC 2 audits, such lifecycle documentation forms the backbone of control effectiveness demonstrations. Access control remains a core pillar of secrets management. Access should always follow the principle of least privilege, meaning individuals and systems can retrieve only the secrets essential to their functions. Administrators managing the Vault must authenticate using multi-factor methods, adding layers of protection against credential theft. Duties should be separated so that no single person can both create and approve secret changes, reducing insider risk. Every access attempt, successful or not, should be logged in immutable audit trails. This level of rigor ensures that if an incident does occur, investigators can trace every action and determine accountability. Logical access control under SOC 2 CC6 is explicitly designed to validate these practices, confirming that sensitive assets remain under continuous governance. Finally, no security program is complete without auditability. Evidence generation for secrets management is built on detailed logs, reports, and samples. Vault systems produce audit logs showing who accessed which secret, when, and for what purpose. Rotation reports confirm adherence to defined intervals. Auditors often sample configuration files or pipeline outputs to verify that no hard-coded credentials remain and that sensitive values appear masked. These records are stored in immutable repositories for later reference. By maintaining verifiable proof of adherence, organizations demonstrate that their security claims are not theoretical but observable, repeatable, and measurable. This capability turns secrets management from a background process into a fully accountable control system. When secrets are exposed despite best efforts, swift and structured incident handling is vital. The response begins with immediate revocation of the compromised secret and rotation of any linked credentials. Next comes an assessment of systems potentially accessed during the exposure window to understand the scope of impact. A root cause analysis documents how the secret was leaked, whether through process failure, tooling gaps, or human error. The entire mitigation timeline, from discovery to closure, should be recorded to demonstrate diligence. Sharing lessons learned with development teams reinforces preventative habits and continuous improvement. Within SOC 2 frameworks, such incident records serve as proof that the organization not only detects problems but also learns from them, embodying the principles of operational integrity and trust. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Testing and validation ensure that secrets management practices are not just designed but truly effective. Periodic penetration tests should explicitly include attempts to identify hard-coded or weakly protected credentials within code repositories and build pipelines. Simulated misconfigurations in CI/CD environments can help validate whether alerts trigger as intended and whether automated remediation works without human delay. For example, a test might intentionally inject a mock secret into a repository to see if scanners detect it and vault systems respond appropriately. Beyond discovery, validation includes verifying that alerts reach the right teams and that escalation paths function smoothly. Capturing these results as audit artifacts provides the hard evidence auditors expect under SOC 2, proving that secret protection operates continuously rather than occasionally. Tooling and automation transforms secrets management from a reactive practice into a continuous safeguard. Integrating Vault APIs directly into CI/CD orchestration enables real-time retrieval and rotation of credentials during builds or deployments. Static analysis tools scan for known secret patterns before code ever leaves a developer's workstation. Policy as code frameworks such as Open Policy Agent can enforce rules automatically, blocking merges that violate credential hygiene standards. Metrics from these automated checks should flow into central dashboards, for example, a Cloud Compliance Manager view, giving visibility to both engineering and compliance teams. The goal is to blend security seamlessly into daily operations, ensuring protection happens by default rather than by exception. To make all of this sustainable, developers must be empowered rather than constrained. Developer enablement focuses on training, clarity, and usability. Teams should receive secure coding education specific to secret handling, understanding not only the how, but also the why behind vault usage and token rotation. Internal cheat sheets and quick reference guides reinforce correct behavior without slowing workflows. Onboarding programs should include explicit no secrets in code commitments, emphasizing that even temporary shortcuts carry long-term risk. Peer reviews and automated checks can reinforce these lessons, providing real-time feedback rather than after-the-fact corrections. By treating developers as security partners, organizations cultivate a culture where compliance is intuitive rather than burdensome. Effective monitoring and alerting form the nervous system of secrets governance. Continuous scans of repositories, build images, and configuration files help detect new exposures before they escalate into breaches. Webhook notifications can automatically alert both security and development teams when a potential secret is detected. Weekly reviews of anomalies ensure that alerts are properly triaged and resolved. Quarterly testing of alert thresholds confirms that the system remains sensitive enough to detect real incidents without overwhelming teams with noise. By keeping monitoring data transparent and actionable, organizations maintain the balance between vigilance and efficiency, a hallmark of mature SOC 2 programs emphasizing operational discipline. In today's interconnected environments, third-party and subservice vendors represent extensions of an organization's risk perimeter. Contracts should require that these vendors maintain vault or equivalent systems for managing credentials, ensuring consistent protection across the supply chain. Vendor SOC 2 or ISO 27001 reports must be reviewed for coverage of secrets management controls. Credential handling clauses should appear explicitly in agreements, defining expectations for storage, rotation, and breach response. Renewals provide natural checkpoints to reassess compliance and address any findings or incidents. This due diligence prevents the weakest vendor link from undermining an otherwise robust internal security program. Metrics and Key Risk Indicators, or KRIs, give leaders a quantifiable view of secrets management performance. Tracking the number of exposed secrets detected each quarter reveals whether prevention measures are improving or degrading. Measuring the average time to revoke after discovery highlights operational responsiveness, a key factor in minimizing damage. Rotation completion rates across environments show adherence to lifecycle policies, while the ratio of automated versus manual secrets indicates maturity. These insights allow continuous refinement of both tooling and policy. Over time, organizations aim to see automation dominate manual intervention, signaling that secret protection is systematic rather than sporadic. During audits, evidence expectations for secrets management are extensive but manageable when processes are well structured. Vault configuration exports and access logs show how control mechanisms function day to day. Rotation policy documents and approval tickets demonstrate governance and accountability. Screenshots or CI/CD pipeline logs with masked values serve as tangible proof that secrets never appear in plain text during builds. Finally, exposure incident records and root cause analyses confirm that the organization not only addresses issues but learns from them. Presenting this evidence as part of a structured audit pack reflects both technical control and procedural maturity, aligning directly with SOC 2's emphasis on verifiable assurance. Despite robust systems, organizations still encounter recurring pitfalls that must be addressed with vigilance. Storing credentials in code or unprotected environment files remains a common mistake, often driven by time pressure or lack of awareness. Missing rotation evidence or incomplete approval records can cast doubt on control effectiveness during audits. Disabling or misconfiguring Vault audit logging removes critical traceability, undermining the very assurance these systems are meant to provide. The remedy lies in automation, continuous monitoring, and strict periodic access reviews. When systems enforce compliance automatically, human error diminishes, and auditors see consistent, trustworthy evidence of control operation. Maturity in secrets management develops through distinct stages. Early-stage programs rely on manual storage methods, often using shared documents or configuration files. The next step introduces centralized Vault adoption, consolidating credentials under controlled access. As automation takes hold, organizations begin rotating secrets dynamically and issuing ephemeral credentials for pipelines. Advanced programs integrate continuous scanning and predictive analytics, identifying anomalies before exposure occurs. At the highest level, secrets governance becomes fully embedded in DevSecOps practices, with metrics and alerts feeding into unified dashboards for executive visibility. This evolution mirrors the broader cybersecurity journey from reactive compliance to proactive resilience. Integration across frameworks amplifies the value of secrets management investments. Vault controls map naturally to NIST SP 800-218's Secure Software Development Framework, reinforcing code integrity and pipeline security. Within SOC 2, these controls support C6, C8, and the confidentiality criteria, ensuring consistent treatment of sensitive credentials across systems. The same evidence can be reused for ISO 27001 audits, FedRAMP assessments, and cloud provider reviews, creating efficiency across compliance domains. Unified dashboards consolidate these insights, helping security leaders present a single, coherent story of control effectiveness. This harmonization demonstrates operational maturity and strengthens the organization's overall assurance posture. In conclusion, effective secrets management spans the entire lifecycle, from discovery and rotation to audit and incident response. Centralized vaults, automated pipelines, and dynamic credentials together eliminate the need for hard-coded secrets, reducing both risk and complexity. Automation ensures that rotation and evidence collection happen consistently, while least privilege access and continuous monitoring maintain security integrity. A strong program does more than satisfy SOC 2 requirements. It builds confidence across development, compliance, and customer communities. As organizations advance, the next horizon lies in extending these protections to endpoint and mobile device management systems, ensuring that secrets remain safeguarded everywhere digital operations unfold.